Welcome to Lecture 7.4, the Laplacian in polar coordinates. Suppose we want to study PDEs in polar coordinates. For example, if we want to solve the heat equation over a circular plate or the wave equation over a circular drum, then we need to translate the Laplacian operator, which is the sum of the second derivatives in Cartesian coordinates. Here's two different ways to write it. The second one is a little bit shorter. So we need to write this guy in polar coordinates, r and theta, where x equals r cosine theta and y equals r sine theta. Think back to vector calculus when we had dA. If we wanted to integrate with respect to area, if we were in Cartesian coordinates, dA was dx dy. But if we were in polar coordinates, all of a sudden dA was not dr d theta anymore, it was r dr d theta. So that's sort of what we're doing here. We're taking a differential operator in Cartesian coordinates and translating it into polar coordinates. First, let's write du dx and du dy in polar coordinates. And we'll do that using the chain rule. So this is a review from vector calculus. I know you're probably a bit rusty in this, but that's okay. So du dx by the chain rule is du dr times dr dx plus du d theta times d theta dx. So this is equal to ur times du dx. I'll write that down in a moment. We're going to figure out what that is, plus u theta times d theta dx. So that we also want to write down what that is. Okay, so recall that r equals the square root of x squared plus y squared, and theta is, well, maybe I should write down why this is. So let's suppose that we have a triangle here, and this is theta, and this is r. This is the x coordinate, which is r cosine of theta, and this is the y coordinate, which is r sine of theta, and this is r. Then r is clearly x squared plus, or r squared is x squared plus y squared. So that's what r is, and theta is the inverse tangent of y over x. So it's the so theta is the inverse tangent of y over x. Okay, and there's other ways you could do that. I'm sure you could write this as inverse cosine and inverse sine. Let's just do it like this. Okay, so what is dr dx? Let's do that one next. So dr dx is, so it's the derivative of this with respect to x. I'm going to do this quickly because, again, it's just calculus. 1/2 x squared plus y squared to the minus 1/2, and chain rule times 2x. And so this is equal to 1/2 times this is the square, 1 over the square root of r squared. So that's 1 over the square root of r squared times 2r cosine of theta. That's what 2x is, 2r cosine of theta. So this, the r's cancel, and we get cosine of theta. Okay, next. Well, let's put that in right here. So that this is cosine of theta. And then next, what is d theta dx? So this, okay, so d theta dx. What's the derivative of this with respect to x? So recall that the derivative d dx of inverse tangent of x is 1 over x squared plus 1. So the derivative of the inverse tangent of y over x, so that's d theta dx, is 1 over y squared over x squared plus 1 times the derivative of y over x. Okay, so the derivative of y over x, so this is just negative. Well, let's see, what is this? So with respect to x, that's negative y x to the minus 2. Okay, So let's write this down. So this is equal to 1 over, so what is y squared over x squared? That's r squared sine over r squared cosine. That's just tangent squared. That's tangent squared of theta plus 1. Again, I'm just putting this into polar coordinates. And now this here, what I need to put here is negative y x to the minus 2 in terms of r cosine and r sine. So if we do that, negative y is negative r sine of theta. And then 1 over x squared is 1 over r cosine theta, quantity squared. So that's over r squared cosine squared of theta. Okay, so things are going to cancel. Things are going to simplify. How do they simplify? So first of all, tangent squared of theta plus 1 is secant squared. So this is 1 over secant squared of theta. And now we have a times a negative 1 over r because of that cancels. And now we have, let's see, what do we have? We have sine of theta times cosine squared of theta. Now, I don't know if you see this or not, but what is 1 over secant squared? That's cosine squared. So the cosine squared with the 1 over cosine squared is going to cancel. In other words, that cancels with that. And what we are left with is negative 1 over r times sine of theta. So let me box that. Okay, so box that. I guess I boxed that one. So we have u theta times negative 1 over r times sine of theta. Okay, so that's du dx. Let's also do du. That's the first one. Let's do du dy. So some of this we can do by symmetry. So du dy, this is du dr times dr dy plus du d theta times d theta dy. Okay, so du dr, that's the same. This is ur. And then what's dr dy? So dr dx was this thing. So we had to take the derivative of this. We got a 2x that popped out. And that x became the cosine, which stuck around. If we do this with y, and same thing, but we have a 2y that sticks out, that'll become a sine. So that actually redoing that, I'm going to say that this is equal to sine of theta. And then du d theta is u theta. And then what's d theta dy? I don't think we can quite tweak this one as easily as before. So let's just do that one here. So d theta dy. So this is, it's the derivative of, where are we? It's the derivative of tangent. It's the derivative of that with respect to y. This is going to be easier because we don't have a 1 over y. So it's derivative of tangent is 1 over y squared over x squared plus 1. So again, that's the derivative of tangent of something is 1 over something squared plus 1. Now, by the chain rule, times the derivative of y over x. And so what's the derivative of y over x? Ooh, with respect to y, I got to be careful with that. Now this is easy because x is a constant, so this is just 1 over x. So this is going to be 1 over secant squared of theta times 1 over x. What is 1 over x? That is, so x is r cosine of theta. So that's 1 over r cosine of theta. And so what is this? This is cosine squared of theta divided by cosine of theta. So this is cosine of theta divided by r. No negative sign this time. So we have cosine of theta divided by r. Okay, so now both of these, well, I'm going to write this. So du dx, here's how I'm going to write this. I'm going to rearrange things a little bit. I'm going to write this. Let's see how to do this. So I want to write it as a differential operator applied to u. So how do we do that? So this is going to be d dr times let's see, actually, let me switch the order of this, just to make things a little easier. Sine of theta times d dr, it doesn't matter, plus cosine of theta over r times, actually I guess it does matter, d theta applied to u. So notice that du dx, this thing right here is just this differential operator applied to u, that's this term, plus this differential operator applied to u, that's that term. Similarly, du dy, oh, I'm sorry, I wrote the wrong one. That's du dy. So, because I was just looking at this right here. So that's du dy, and du dx is, let me do this. Let me box this. And the du dx is going to be up here. How about if I just actually write that up here? I think I have more space. So du dx equals cosine of theta times d dr minus 1 over r sine of theta times d theta applied to u. Okay, so that is important as well. Okay, so we're going to use this right away in the next slide. Now that we've computed d dx and d dy in polar coordinates, the Laplacian is just the sum of the squares of these operators. So in other words, d dx is cosine theta d dr minus sine of theta over r times d theta times cosine of theta d dr minus sine of theta over r d theta. And I know I didn't do anything but just write this thing twice, but psychologically, when we multiply these out, I think it helps to do it like this. For me anyways. Okay, so let's write this out. So it's just like we're multiplying polynomials. It's this times this. So this is cosine of theta times d dr times cosine of theta times d dr. Next, let's do cosine times that term. So this is cosine of theta times d dr times, well, this is minus, so I'm actually going to make that a minus there. So sine of theta over r times d theta. And now what's next is this term times that term. So this is minus sine of theta over r times d theta times cosine of theta d dr. And finally, the last one is the product of the last two terms. So that's minus and minus, so that's plus sine of theta over r d theta times sine of theta over r times d theta. Okay, so how do we simplify these? So for a lot of these, we're going to have to do the product rule. Well, so this is the DDR of this product. Now, anytime we have a cosine of theta, we can pull that right out here. Because theta, or DDR of anything, theta is a constant, so that goes out. So this I can write as cosine squared of theta times DDR of DDR, so that's d squared over dr squared. Okay, let's do this one now. So what can we pull out? We have a dr here. We can pull out the sine of theta. So we can say minus cosine of theta sine of theta times times what? So times, how about if I just do d dr times 1 over r d theta. And we need the product rule for this. Even though this is a theta, it's still a differential operator, so we can't pull that out. Okay, so next we have minus. What can we pull out here? We have a d theta. We can't pull out either of these. So minus, so I'm just going to leave this, minus sine of theta over r times d theta of cosine of theta d dr. And then the last one, we have plus, so what do we have here? We have a d theta here. We can pull out the r, not the theta. So we can write this as sine of theta over r squared and then d theta times sine of theta d theta. Okay, so this one is fully simplified. So let's write this as, this is cosine squared of theta d squared dr squared. Now what's the second one? So this is minus cosine theta sine of theta. Let's make sure that looks more like a theta. And now by the product rule, so the product rule I'm going to do for all of these, the first one times the derivative of the second one, and then vice versa. So the first one is 1 over r times the operator applied to the second one is d squared dr d theta, and then plus the opposite, the derivative. The derivative of the second one is minus 1 over r squared times the second term, which is d theta. So again, this is dd. So this plus ddr of that plus ddr of that times that. Okay, so just the product rule. Next, we have minus sine of theta over r times, now we got to do the product rule in here too. So cosine of theta times d theta of d theta of ddr, which is d squared dr squared, and then plus the derivative of cosine, which is sine, so that's minus sine of theta times the second term dr. So again, it's messy, but it's very straightforward. And finally, we have plus sine of theta over r squared times, then the product rule on the inside is, so sine of theta times d squared d theta squared, plus the derivative of sine, which is cosine of theta times d theta. Okay, so now let's simplify this. So what do we have here? I think some of these terms are either going to add or cancel. So we have cosine squared of theta times d squared dr squared. Let's make sure that's a 2. And now what else do we have here? So I think we're going to have some, so cosine sine over r times the mixed partial. I think we have another one of those. I saw, where was it? It was, here it is, cosine sine over r times the mixed partial. So this is going to be minus 2 cosine theta sine of theta over r times a mixed partial. That's d squared over dr d theta. And now what else do we have here? We have a couple of them that are over r squared. So here we have cosine sine over r squared times d theta, right? And we have that somewhere else as well, I think, right? I thought I saw it. Yeah, cosine sine over r squared times d theta. And these are both positive. So this is going to be plus 2 cosine theta. I swear this is going to cancel very nicely. I think you're going to be surprised. Over r squared times, what was that, d theta? D theta. Then what else was there? There's a sine, there's a sine squared of theta here. So sine squared of theta over r. So that's a plus sine squared of theta over r times dr. And what else do we have? So what have we used? So we've used that term. We've used both of these terms. We've used that term. And we used that term. And now I'm trying to remember what we have used. Maybe we have everything. Is there something that we are missing? This is, oh no, there's a sine squared over r squared right here. Yeah, it's easy to skip. We use that one. We have not used this one. So finally we have plus sine squared of theta over r squared d theta. Okay, the home stretch, I can see the light. Okay, so this is d over dx squared. Okay, I'm just making sure that, so it's this term, and this term, this, and this. Now, I'm not going to do the same thing for d dy. It's actually very similar. Instead of, I'm just going to, I did it in advance, and I'm going to tell you what it is. So d, because again, it's going to be 8 minutes or 9 minutes of messy chain rule stuff, but it's straightforward. So what you end up getting is you get sine squared of theta times d squared dr squared. You get a plus 2 cosine of squared sine of squared over r times d squared dr d theta. You get a minus 2 cosine theta sine of theta over r squared d theta. And then you end up getting instead of a sine squared here, you get a cosine. I'm lining these up vertically so you can compare them. So you end up getting a cosine squared of theta over r times d dr. And then you end up getting a cosine squared of theta over r squared times a d squared d theta squared. So if you add these things up, what is going to cancel? So these two things cancel. These two things cancel. And we're left with, well, what are we left with? Well, when we add them up, we're going to get a lot of sine squareds and cosine squareds. So we add these two things up, we actually just get d squared over d r squared. So that gets 0. We get 0 there. And then here, what do we get? We have sine squared plus cosine squared is 1, but we're over r, so we have 1 over r times d dr. And then what do we have here? We have another sine squared plus cosine squared, but we have over r squared. So we have a 1 over r squared times d squared d theta squared. Okay, so the Laplacian operator in polar coordinates, if I want to write it short, I'm going to write it as dr squared plus 1 over r dr plus 1 over r squared d theta squared. So this is, again, my little shorthand way to write this. And so, in other words, the Laplacian of u is urr plus 1 over r ur plus 1 over r squared u theta theta. So it's not quite the sum of the second partials in polar coordinates. Okay, so this is the Laplacian of u in polar coordinates. Now that we've computed the Laplacian in polar coordinates, and it's given by this formula, or here's the shorthand version of it, our next goal is to find the eigenvalues of the operator, which correspond to the fundamental frequencies, and the eigenfunctions of the operator, which corresponds to the fundamental nodes. So to do this, we have to solve the Helmholtz equation in polar coordinates. Recall that we did this recently in Cartesian coordinates. Naturally, this depends on the boundary conditions. Clearly, in theta, the boundary conditions have to be periodic. Whatever your function f or u is, f of r and theta plus 2 pi has to equal f of r and 2 pi. However, in R, we have several choices for the boundary conditions. So if we have a circular region, we can specify the temperature at the boundary. And if we do that, we get Dirichlet conditions. It doesn't have to be 0, but that's the simplest example. If we insulate the boundary of the circular region, then we get Neumann boundary conditions. That means that the rate of change of f with respect to r is 0. Or we could get mixed boundary conditions, so some linear combination of these first two. And by making these equal to 0, of course they don't have to be 0. This is what they are if the boundary conditions are homogeneous. We will only consider Dirichlet boundary conditions in this lecture. In the next example, we will actually solve the Helmholtz equation in polar coordinates with Dirichlet conditions. Recall when we did this for Cartesian coordinates, then we did them for Neumann and mixed. We're only going to do it once here. Here is that promised example. We're going to solve the following boundary value problem for the Helmholtz equation in polar coordinates. So that's the Laplacian of f, which is this creature in polar coordinates, is equal to negative lambda f. So we want to find the eigenvalues lambda and the eigenfunctions f. And then we have two boundary conditions. The first one are Dirichlet boundary conditions in R, and the second one are periodic boundary conditions in theta. So again, think of this as modeling the temperature of a disk, and the radius is equal to 1. And think of F as being the temperature. So this says the temperature along the entire boundary is fixed at 0 degrees. Okay, so we're going to solve this like we solve all of these PDEs, by separation of variables. There'll be a few small differences because this is an equation that we have not seen before. But I'm going to go through the basic steps pretty quickly. So we're going to assume that our function f separates as a function, let's say big R of little r and big T of theta. And then we're going to plug this thing back into here. So let's plug back in. Now I'm not going to write down what all the derivatives are. I trust at this point you can do this in your head. You can see that f RR is just R double prime T, and then we have 1 over R times FR, so that's just R prime T, and then we have plus 1 over R squared times F theta theta, that's just R T double prime, and this is equal to negative lambda times F, which is RT. Okay, so let me, before I go on with this, do these zero boundary conditions. So this first condition says that if f of 1 theta, that's r of 1 times t of theta, and if that's equal to 0, then as before we have a number times a function being 0 everywhere, so that number has to be 0 because the function t is not 0. So r of 1 equals 0, and similarly we have this boundary condition here. I'm going to do this. How about if I do this? So right here, that is going to be equal to, so f of r and theta plus 2 pi is big R of r times big T of theta plus 2 pi. And since that's equal to f of r and theta, which is equal to r of big R of little r times T of theta. So we now have these two things are equal. So r times, so this function times T of theta plus 2 pi equals the same function times T theta. So what do we conclude? We conclude that T of theta plus 2 pi equals T of theta. So let's write that down. So we get T of theta plus 2 pi equals T of theta. And it should make sense why this is true. Our function f is periodic in theta, and so if it splits up as a function of the radius and a function of theta, then that function of theta better be periodic radially as well. Okay, so these are our boundary conditions. Now we already plugged back in, so let's simplify. So we're going to divide both sides here by 1 over r squared RT. And so 1 over r squared RT. So let's see. Here's what I'm going to do. I'm going to, all in one fell swoop, I'm going to cancel these terms and separate variables. So let's put everything in R on the left-hand side. So let's see. So what do we have that's in R? So these R and T's are going to cancel with, so that T is going to go away, that T is going to go away, that R is going to go away, and then both of these are going to go away. Okay, and I don't know how to signify I'm canceling one of these things. So anyways, it's not hard to check that this, let's just do it ourselves, so this is R squared times R double prime over R, little r squared times big R double prime over big R, plus little r times big R prime over R. So these are the first two terms. And then the third term is going to be this lambda. So this is going to be plus lambda times r squared. And then What's the thing in t? That's right here. So that's t double prime over t. The r squareds cancel. So we have that's equal to negative t double prime over t because we're moving it to the right-hand side. So now we have this quantity in r. This does not depend on theta, and it's equal to this quantity in theta that does not depend on r. So it has to be a constant. So let's call that constant nu squared. You may say, well, why did I put the squared there? Well, look at this equation right here. That should tell you. So we get two ODEs. We get one of them in t. So we get t double prime equals negative nu squared t. And our boundary condition is periodic. So t of theta plus 2 pi equals t of theta. And then our second ODE is an r. So that's, let's see, what is that? That's r squared r double prime plus r prime plus theta times r squared minus nu squared r equals 0. And then we have a boundary condition that r of 1 equals 0. Okay, so we have seen both of these ODEs. This first one, you should look at this and say, so these are 2 pi periodic functions that are sines and cosines. Nu has to be equal to n, and t, n of theta, has to be an cosine of n theta plus bn sine of n theta. So we don't have we have periodic boundary conditions. We don't eliminate either the sine or the cosine. We just know that the frequency has to be an integer n. Okay. So what else do we know? Its frequency is 2 pi over n. Yeah, this coefficient has to be n. That's what we know. The next one. This has a name. This is parametric Bessel equation. And I hope you've seen this before because I introduced this. So a little history in one of our earlier lectures called Bessel functions, or Bessel's equations. This is after we studied power series solutions. We solved Bessel's equation, which is this equation. It's just without the lambda. And we got these things called Bessel functions of the first kind and the second kind. So please watch that lecture if you have not already. Later in the class, I think I called it special orthogonal functions. I showed you a whole bunch of functions like Chebyshev's equation, Hermite's equation, Legendre's equation, might be another one. Oh, and one of them was parametric Bessel's equation. So this one with the lambda. And in this lecture, I didn't actually solve any of these. I just told you what the solutions were because I wanted to show you what these generalized Fourier series coming from Sturm-Liouville theory were about. And so I actually solved this, or I gave the solution without actually solving it. And so technically, I didn't actually solve this. So I probably should tell you how to solve this thing. Well, you could do it like we did Bessel's equation, but there's actually a very simpler way. We can do a change of variables to turn this into Bessel's equation. And let me just show you how to do that. So we'll change variables. I'm going to let x be equal to square root of lambda times r. And then by the chain rule, we get that d big R, d little r, you have to be careful, is d big R dx times dx dr. And so that just reduces down to the square root of lambda times dr dx, because this guy here is root lambda. Okay, so then what else? This also tells us that r equals 1 over root lambda x. So now if we write this instead of using r as with x, then let's see what we get. So first of all, we have an r squared here is going to give us a 1 over lambda, but this r double prime is going to give us a lambda, because if we take two derivatives d of r here, we're going to get a root lambda squared popping out, so just a lambda. So this term is going to just be x squared r double prime. This next term, we're going to have this r, we're going to have a 1 over root lambda here and a root lambda here. Those will cancel, so we get a no change. So we get x r prime. And then the change is going to be here. R squared is just x squared over lambda, and then a lambda here. And so this turns into x squared minus nu squared times r equals 0. Let's not forget our boundary condition. If I have room for it, r of 1 equals 0. So this thing here is the ordinary Bessel's equation, and these solutions are Bessel functions. Again, go back to the old lecture on Bessel's equation if you have not watched it. I will refresh your memory on the solutions to Bessel's equation on the next slide, but for now, let me just say that we have found a solution for each n. So let me write that down. So for each n, we have a solution fn of r and theta, which is rn of r times tn of theta, which is, so I'm going to write these in opposite order, an cosine of n theta plus bn sine of n theta times a Bessel function, jn of omega nmr. So if you're a little rusty on that, especially what that omega is, that's what we're going to do in the next slide right now. Although before we go there, since I have this all written out here, let me just remind you that omega nm is the mth root of the nth Bessel function jn of the first kind, and the square of this is the eigenvalue lambda here of this Sturm-Liouville equation. So in other words, this lambda, let me write it up, this lambda here, the eigenvalues are of the form omega nm squared. And if the radius were not equal to 1, we would have to divide by, let's say the radius were a, would have to divide by, I think it's either a or a squared. But just to make things as simple as possible, we're going to assume that the radius is 1. Here's a summary of what we've done so far. To solve the heat equation over a circular plate, or the wave equation over a circular drum, we need to translate the Laplacian, which in Cartesian coordinates is the differential operator, which is the sum of the second partial derivatives, into polar coordinates, r and theta, where x is r cosine theta and y is r sine theta. This becomes the following operator: 1 over r times ddr plus d squared dr squared plus 1 over r squared d squared d theta squared. And here's a slightly shorter way to write it, if you prefer. There is a 2-parameter family of eigenvalues of the form lambda nm, which is omega nm squared. And we saw that the following is an eigenfunction. So an cosine of n theta plus bn sine of n theta times jn of omega nm r. So if this is an eigenfunction, we can break these into 2 different eigenfunctions. One of them is cosine times this Bessel function, and the other one is sine times the Bessel function. So we'll call the first one fnm of r and theta, which is cosine n theta times jn of omega nmr. And the second one, we'll call it gnm of r theta, which is sine of n theta times jn of omega nmr. Once again, omega nm is the mth positive root of jn of r, which is the Bessel function of the first kind of order n. These eigenfunctions, the f's and the g's, together form a basis for the solution space of Helmholtz's equation, which is the Laplacian of u equals negative lambda u. And of course, this is in polar coordinates, where the radius is 1. They're slightly more complicated if we have a different radius. I think we have to divide by an a in here. As such, every solution, so a function h of r and theta under these Dirichlet boundary conditions, can be written as a linear combination of the eigenfunctions, the f's and the g's. So I'm starting from n equals 0 because when n equals 0, we get a constant term here, and so we get a non-zero term here, though I should specify that we should not allow n to be 0 there should not be a b0, 0 term because we get 0 when n equals 0, and then we would destroy uniqueness. So it's not quite as elegant to write that, but I think, so I'll just leave it like this. So given this, we can factor out this Bessel function, and we can write this as this infinite sum over all n and m of this Bessel function Jn of omega nm r times a n m cosine of n theta plus b n m sine of n theta. That is, every solution h to the Helmholtz equation in polar coordinates with Dirichlet boundary conditions can be written uniquely as a linear combination of the eigenfunctions, which we can write more simply like this, and this is called a Fourier-Bessel series. We saw these things in a previous lecture. By orthogonality of these eigenfunctions, due to Sturm-Liouville theory, and the identity that I did not tell you about earlier because, frankly, I forgot about it, which is if you take this function, Jn of omega x, and you compute its norm squared, which by definition, which is the inner product of this Bessel function with itself. And if you recall from the lecture on special orthogonal functions, that this is defined with respect to an integral and a weighting function that came from the Sturm-Liouville problem, w of x equals x. So in other words, it's the integral from 0 to 1. That's the range of the radius, r, which actually down here we're calling x, of the Bessel function times itself. And then this x is the weighting function w of x. And remarkably, this integral has a very nice closed form solution. It's 1/2 times the j plus 1th Bessel function squared evaluated at omega. So I don't expect you to remember this. I did not remember it when I recorded the previous lecture. It's just there's a huge table of tons of Bessel function identities. It's amazing. I encourage you to look them up. This is one of them that helps us. So what does this mean? Well, we have a nice formula for the norm of a Bessel function. So these coefficients a and m up here are just the projection of our function h onto the eigenfunction f and m. So that's h dot f and m over f and m dot f and m. And that is the integral over the unit disk of h times f and m dA. Now I haven't defined the actual inner product because these are now two-dimensional functions, so I'll tell you that this is what it is. And then we have to divide by the norm of f and m squared. This is also going to be an integral of this big function over the unit disk. By orthogonality, this reduces down to the integral of just the Bessel functions. I have not convinced you of that. I am not going to. Again, it's very messy. So this thing ends up being this creature. So let me unpack this a little bit. So right here, this is just the integral of h times f n m over the unit disk. That's what this is here. I've just put it into polar coordinates and put in limits. And then what do we have here? This norm of f and m squared reduces down to just the norm squared of the Bessel function, which is this formula. And if you divide by this, you get 2 over, that's exactly what, so this thing here ends up being this. And again, I've glossed over a few details, but I think that's fine. Similarly, b and m is the same thing. It just replaced these f and m's with the g and m's. So you get a similar quotient, and you end up getting a similar formula. You just have signs instead of cosines. Let's finish with a few pictures of Bessel functions and what these eigenfunctions in the disk actually look like. So recall from a previous lecture that this formula was what the Bessel functions actually were. Don't think about that too much. But pictorially, here's what the first 6 of them look like. And recall that omega nm was the mth positive root of jn of x. So for example, this is omega 0, 1. This is omega 0, 2. This is omega 0, 3. And then J1 is this pink curve, so this is omega 1, 1, omega 2, 2, and so forth. Okay, so the next slide, I'm going to take this J naught, this red curve, and I'm going to dilate it and show you what that looks like. We've seen this picture in a previous lecture, but I think it's worth revisiting it. So we're going to create a Fourier-Bessel series from this Bessel function J naught of x, which is given by this formula right here. So in general, a Fourier-Bessel series is just a linear combination of dilates of Bessel functions, possibly with other functions like sines and cosines that we saw. So in this case, we're dilating it where these omegas are the nth root of this function J naught. So this J naught is this blue function here. It was the red one on the previous slide. So this is J naught of, let's say that omega naught is 1. So J naught of x. This pink one is J naught of omega 1 x. The next one is J naught of omega 2 x. J naught of omega 3x, and you get the idea. So these things are actually solutions to the following Sturm-Liouville equation, which is why we did see this in a previous lecture. Finally, I want to compare the eigenfunctions and eigenvalues of the Laplacian in the unit square to those of the unit disk, both of these with Dirichlet boundary conditions. We'll start with the unit square, where the eigenvalues, as we've seen, are n squared plus m squared. And the corresponding eigenfunction is sine nx times sine my. So think of sine nx as being the sine wave in the x direction, let's call it this way, and sine my as being the sine wave in the y direction. So in this first case, this is when n equals 1 and m equals 1, and the function is sine of x, sine of y. In the second example, this is n equals 1 and m equals 2. Again, think of this cross-section as sine of 2y, and this cross-section as sine of x. And finally down here, this is n equals 2 and m equals 1, so we have sine of 2x times sine of y. And you can easily see the pattern for what these higher frequency eigenfunctions are as well. So think of these as like the fundamental vibrating nodes. This is the two-dimensional analog of sines and cosines, or of a Fourier series in Cartesian coordinates. At last, we come to the unit disk. The eigenvalues are omega nm squared, the roots of the Bessel functions, and the eigenfunctions are of the form cosine n theta times jn, I'll call this of omega r, and sine n theta times jn of omega r. Here's a picture of 9 of them. Let's try to understand which is which. So notice that cosine and sine are just functions of theta. So if you go around, if you fix a radius and you go around, you can figure out which is which. Over this first one, if you go around at a fixed radius, it's constant. So that means that this cosine term has to be a constant. So here n equals 0 for all 3 of these. So this first one is when m equals 0. That's a cross section. If you slice it right here down this way, you get that Bessel function J naught, the first one there. So this second one, the Bessel function, is That's the dilated version. So this is n equals 1. This is m equals 1. And this is m equals 2. So this is going to be n equals 1, n equals 1, n equals 1. And this is n equals 2, n equals 2, n equals 2, m equals 0, m equals 1, and m equals 2, m equals 0, m equals 1, and m equals 2. Now you may be wondering, well, which one of these is sine and which of these is cosine? Well, for n equals 0, we don't even have a sine term, so that's easy. But what about the others? Well, what's the difference between a cosine and a sine? It's just a phase shift by 90 degrees. So it doesn't really matter which one of these you consider the cosine or the sine. If you rotate it 90 degrees, you get the other one. So it just depends as to where you want to orient your x-axis versus your y-axis. So these things are the analog of those fundamental nodes that we saw in the unit disk, or sorry, in the unit square, which was like a 2D Fourier series. Think of this as a two-dimensional polar Fourier series. So these are the fundamental nodes, and every vibrating drum, every wave solution to the wave equation in polar coordinates can be written uniquely as a linear combination of these guys. Well, or at least the initial condition can be written as a linear combination of these, and then as time goes on, that's going to be fluctuating, so we'll have to multiply that by some function of time, which is also going to be a sine and cosine. And that's what we'll do in the next lecture. And we'll also do it for the heat equation. So stay with us.